I wanted to start by talking about alternate notations for derivatives, because I'm going to use some of these alternate notations other than the prime notation as we move forward here. So we're already familiar with the derivative of f of x, this phrase being represented by f prime of x. You could also think of it, you could also do it by writing it with this d dx notation, or this big D notation, which I'm particularly fond of. And the idea here is that this d dx and this dx are operators. They're acting on the f of x, sort of like how the square root sign is acting on 9, where the square root of 9 as a whole is the result of having applied this somehow action of a square root to the number 9. Likewise, dx applied to f of x, d dx applied to f of x. In both cases, this little x down here explains what variable we're interested in, whereas this prime notation lacks that ability to really specify what it's interested in. For what it's worth, this is often described as prime notation. This is Leibniz notation after Gottfried Leibniz, one of the co-inventors of calculus. And then this dx, that doesn't really have a name, but I just call it big D notation. You should be aware there are other ones as well. If we're thinking about the derivative of just some y, like it's y equals f of x, like y equals x squared, you'll often see y prime. You'll see d dx of y, or more commonly dy dx. These dy and this dx are differentials. We're going to see those again in integration, and they have their own little meaning. But it's really a modification of that delta x, delta y that we've talked, delta y, delta x notation. This idea of change in y divided by change in x. This highlights the slopiness of a derivative, where instead of deltas, it's a little d, which in Leibniz days he was thinking of as a super tiny number in the y direction, or a super tiny number in the x direction. Not quite rigorous, but it was good enough in the 17th century. And then this dy notation, this dx notation, you'll sometimes see that as a like that, although this is rare. But you'll see this, and this all over the class. This dx dy, dxy, you're not going to see so much. But then, if it were with respect to time, you'd be seeing d dt of f of t, which is the same as f prime of t. And you'd want things like this if, for example, you're trying to take the derivative of a t cubed, where you want to specify, oh, I want t to be the variable, not the a. And so then that would be a times, well, we'll see what that is in a bit. Well, it'll end up being 3a t squared via methods that we'll develop soon.